Hello, and welcome to section 6.2 of our linear algebra notes. Today we're going to talk about orthogonal sets and orthogonal matrices. We'll compute orthogonal projections, and we'll understand orthonormal sets and orthonormal bases. So first of all, if we have a set of vectors in Rn, it's said to be an orthogonal set if each pair of distinct vectors from the set is orthogonal. That is, when you take the dot product of any two different vectors in this set, you always get 0. If we want to test if a set is orthogonal, well, the only way this set can be orthogonal is if every single dot product is 0. So to show orthogonal, we have to show that all of them are 0. And in fact, if we show that any dot product within this set is not 0, then we don't have an orthogonal set. And if you look at this, the second and third vectors of this set do not have, I believe that's -30, they do not have 0 as their dot product. So we can actually just stop right here, and this is not orthogonal. If those were 0, we would have to go through and test all the other ones to make sure that we get an orthogonal set. And I should mention that the others do have dot product 0. Okay, so now we have a theorem. If we have an orthogonal set, in fact, that set is linearly independent, which is nice because if it's linearly independent and it spans some space, then it's a basis. So if we have a span of vectors that are orthogonal, then we automatically know that that set of vectors themselves is a basis for the space. So let's go ahead and prove that these vectors are linearly independent. So recall that to test linear independence, we take a linear combination of our vectors, we set it equal to 0, and we see if we can find a non-trivial solution. So what we're going to do is we're going to actually take a dot product of the left-hand side with, we'll start by dotting it with U1. And then on the right-hand side, we're going to have to do the same thing. So we can use the distributive property of dot product to distribute that U1 across that sum. And that is theorem 1b. And the dot product of the 0 vector with anything is just 0. Okay, and because you're multiplying each component by 0. So now let's look carefully though at each of these little pieces. All of these products, except that very first one, are going to be 0 because this is an orthogonal set. So what this means is that we have C1 times U1 dot U1 plus a bunch of zeros. And so this is, since these dot products are always going to be 0. But U1 dot U1 has to be non-zero because theorem 1D says, and so let me just write that over here. Theorem 1D implies that U1 dot U1 is not equal to 0. And that's because we're starting with a non-zero vector. U1 is non-zero, so its dot product with itself has to be positive. So that means that we can divide both sides. Oh, and that should be a C1. Okay. We can divide both sides of this equation by U1 dot U1. It's okay to divide by that because it's not 0. But when we divide 0 by something non-zero, we get 0. So C1 equals 0. And in fact, you can repeat this process. You can dot the whole thing with U2 to get C2 equals 0, and so on. And so ultimately, you get only the trivial solution. And so, in fact, these vectors are linearly independent, as we wanted. Okay. So now that naturally motivates the notion of an orthogonal basis. So an orthogonal basis is just a basis that also happens to be an orthogonal set. So you could have a basis whose vectors are not necessarily orthogonal. For instance, if we went with R2, it has lots of different bases, but one example would be the basis 1, 0, and 1, 1. Those are not orthogonal because 1, 0, dot 1, 1 equals, equals just 1. So not every basis is orthogonal, but the ones that are nice. And so here's a nice theorem that tells us if we have an orthogonal basis, we have kind of a shortcut for how to find the coefficients when we want to write a given vector within our basis. And so let's go ahead and try that calculation. It has to do with these dot products. So if we want to express our vector negative 6, 3, so that's taking the role of our y here, well, then what we need to do is we need to take its dot product with u over u's dot product with itself times u, and then plus the dot product of our vector with the second basis vector over the second basis vector dot producted with itself times that second basis vector. And what we'll do is we'll do the coefficient of u together, and then for the quiz, you can do the coefficient of v. So here for u, we want to do our vector x, which is negative 6, 3, dotted with u, which is 3, 1, over u dotted with u. And so that's going to end up equaling negative 18 plus 3 over 9 plus 1, which gives us negative 15 over 10, or negative 1.5. And now for the quiz, go ahead and enter your answer as a decimal. That will be easier, I think. Okay, so one important notation, and this is something that will come up for a decent amount for those of you who are statistics majors. If we have a subspace spanned by a given vector, then the orthogonal projection of that vector onto, technically it's onto the subspace L, but it's often shorthanded by saying U when you just have one, when L is just the span of one vector. So this is the orthogonal projection of Y onto U. Okay, so this is essentially the what we did up above when we expressed our vector in terms of our basis vectors. It's kind of like we wrote a coefficient times our first basis vector, which is in some sense a projection. So remember, projection is just kind of like dropping down to a piece of that. And we'll see a visual of this geometrically in just a moment. But let's go ahead and do this computation so we kind of see what it looks like. So if we want to project y onto u, we do y dot u over u dot u times our vector u. And so in this case, we have 14 plus 6 over 49 plus 1 times 7, 1, which is what, 20 over 50 times 7, 1. So that's 2/5 of this vector, or we could write it as 14/5 and 2/5. And so note that this is a multiple of u. And that's exactly what we mean by a projection. We're saying we are taking our vector y and dropping it down to u. Okay, so if we want to write y as the sum of two orthogonal vectors, well, we can write one vector in the span of u. And in fact, remember the span of u is all multiples of u. So that's exactly this vector y hat. And well, if we want to write y as the sum of y hat and something else, well, the easiest something else we can use is just y minus y hat. In fact, that's the only option, right? Because we need it to be something that adds up to y. And so then this means that we're claiming that y minus y hat is orthogonal to u. So let's do this computation, and then we'll look at why it's always true that y minus y hat is in fact orthogonal to u. So here we have y equals y hat plus y minus y hat. And so we just take 2 minus 14 fifths gives us negative 4 fifths, and 6 minus 2 fifths gives us 28 fifths. And of course, the 2 on the right-hand side add up to 2 sixths. Okay, so let's test that y minus, and that should have a bar over it, that y minus y hat is in fact orthogonal to u. So that means we need to take the dot product of y minus y hat and u. So here we go. Let's do what y hat is. So that's the dot product of y with u, and then just times u. And we're taking the dot product of all of this with u. Well, again, we can use the distributive property of dot products. And hopefully I'll remember all my little bars here. And here, so notice that we had this guy dotted with u, so we did this dot with u. But now we have a u dot u and a u dot u. They cancel out, and what we're left with is y dot u minus y dot u, which equals 0. And so that tells us that those two are orthogonal. Okay, so now for your quiz, I'm giving you a suggestion for how you can check your answer. We claim that these two vectors, y hat and y minus y hat, are in fact orthogonal. And so I'm claiming that we can test that by taking their dot product, and I'm asking you, what should that dot product be if you've done this correctly? Okay, now let's look at this geometrically. So we have, let's say we have two vectors, negative 2, 3. So here is our u, and our v is 3, 2. And you can kind of see here that those are orthogonal. And remember that in R2, orthogonal really means that they meet at a right angle. And now we have a vector y, 1, 4, 2, 3, 4. So here's our y. And so there's our vectors along our coordinate plane. And now this exercise asks us to compute the projection of y onto u and also the projection of y onto v. So this is the same idea as before, but I'm going to give that a little subscript so that we know which projection we're doing. And we do y dot u over u dot u. And this is the third time in these notes that we've done this. So I'm going to go ahead and let you work it out. You can pause the video and just try it and see, make sure you get the right answer. And then we can also do y v, and that use the same formula but with v instead of u, and you should get 11/13. And so what this means then is if we take the projection, let's do this projection, oops, I wanted a different color here. Let's do it in green. If we take the projection of y onto u, we're getting sort of part of the way down our u. We're getting to maybe here. And you should notice it's kind of like when you take a projection down onto the x-axis, you sort of look at the shadow that you would get if the sun was coming perpendicular to you. And as the sun comes perpendicular to you, it drops a line down from the tip of y, and that is the tip of your projection. And then the same thing goes for the projection onto v. And that's a little bit, I know this drawing's not perfect, but that's a little bit farther along v. And one thing you should notice about this is that when you add the projection, so here's our y hat onto v, here's our y hat onto u, when we add those up, we get y. So really what we're doing is we're breaking our vector into two orthogonal components based on that basis there. So it's kind of nice because then we're thinking about our vector as the sum of two things that are like perpendicular. Okay, so our last new concept is something called orthonormal sets. So a set is orthonormal if it's a set of unit vectors. And remember, a unit vector means that its dot product with itself is 1. So let me just write that as u dot u equals 1. So our first quiz asks whether the set given, these two vectors, is orthonormal. And let's call these u and v. So what you need to do to test these is you need to test three things. So first of all, you need to test that u dot v is 0. That's the orthogonal part. And then you need to test that u dot u equals 1. That's the unit, which sometimes we're, unit vector thing, which sometimes is where the normal comes from. And same thing with v dot v. Okay. So now if we have a matrix that has orthonormal columns, well, that happens if and only if the matrix transpose times itself equals the identity. And by the way, if u is square, we call it an orthogonal matrix, which is super confusing notation. I think that it ought to be called, in my opinion, it should be called an orthonormal matrix, because you can't just have orthogonal columns, they have to also be unit vectors. So that's kind of unfortunate notation, but just be aware of that. Hopefully that will help you avoid any confusion with it. So let's prove this. So if we have, let's let our matrix be U. If we just have an arbitrary m by n matrix U, well, if we write down U transpose times U, that's going to look like we take the transpose of each column and we multiply by the matrix that has those columns. And so what we end up with a big matrix. We have U1 transpose times U1, then U1 transpose times U2, all the way through to U1 transpose times UN. And then we repeat with our second row, U2 transpose times that first vector, U2 transpose times that second one, and so on and so forth. But if you go back to 6.1 and recall, the definition of the dot product is the vector transposed times itself. So in fact, this is just a bunch of dot products in our matrix. It's U1.UN, U2.U1, U2.U2, and so on and so forth. Well, kind of what's nice about this is if our columns are orthonormal. Oops. This happens if and only if, first of all, we need the dot product of any column with itself to equal 1. These are the entries along our main diagonals. And we have one other thing that we need. We need anything that's not dotted with itself, this is the orthogonality part, must have dot product 0. And so that means that everything else has to be a 0. But that just gives us the identity matrix, because that's the matrix with 1s down the main diagonal and 0s everywhere else. Okay. And so finally, we just have a theorem that tells us some information about how these things work. So we have a size of u at times any vector doesn't change the size of that vector, the length of that vector. It doesn't mess with dot products, and it only equals 0 if the dot product was 0 to begin with.